Hello, good afternoon, everyone. Can you hear me? If you can hear me, just show me a thumb up. Very good. I can see your signs. It's very nice meeting with all of you. And you're welcome to the University of Ibadan, the first and best. Yeah, very good. I can see your thumb up. Yes, so this meeting is also going on live on YouTube. We are both here and also on the YouTube. So for those who also want to follow us on YouTube, it's fine. Or maybe you have some of your friends who may not have access to this session, maybe due to the limitation of space and that, you may try and follow us also on YouTube. Okay, let me paste the link to the YouTube platform here. Okay, so you can follow us also on YouTube. My other colleague will have introduced you to what we do in the Department of Chemistry. I'm trying to see, can everyone hear my voice? Oh, good. Very great. Yeah, that's great. Okay. So in chemistry, one of the things we do is that we introduce you to what chemistry is all about. And when you get to your different departments, you can apply the chemistry, whether you are in the Faculty of Agriculture or Renewable Natural Resources, or you are from the medical line or from technology, whichever field you are coming from, or even basic medical sciences or College of Medicine, or maybe you are from sciences, wherever you're coming from or education, you can apply the chemistry to any part you are coming from. I think some are saying they cannot hear my voice. Okay, just want to be sure that everyone can hear me. Oh, okay. All right. So welcome again to the Department of Chemistry. And in the next couple of minutes, we'll be looking at a concept that most of you are familiar with. Okay. Yeah, if it is breaking, you may need to check your network signal, the network strength, whether it is strong enough or not. All right, so let me share my screen with you. All right, I hope you can see my screen. Yeah, hopefully you can see my screen. So my name is N.D. Ojo. Some of you might have seen my name maybe on the LMS platform, or maybe some of your senior colleagues might have informed you about me. Yeah, so this is my name, and I guess you can see my face also. Okay, maybe one of these days we'll get to see one another physically. I can see that some of you are still joining the class. So before we move on, let me say that this aspect of chemistry is basically about acids, bases, buffers, salts. We can also look at chemical kinetics and radioactivity. But due to the limitation of this period, and we are just introducing you to chemistry in the university, I will only be restricting it to acids and bases. And we are also going to maybe look at some calculations together. Let me also say this before we move on, that chemistry is very interesting. And it's also easy to grasp, only that it requires a lot of diligence, hard work. It requires being able to search for information. Sometimes we need to go online and watch some videos or maybe read some textbooks. So all those things can help you. But let me say it again. Okay, let me say it again that this chemistry course, C-CHM 101, is a course in which you can get 100%. And I'm very frank with you. It's a course in which you can score everything. And if you get 100%, that is what you have just got. And that is what you'll see as your results. Okay, let me record this session. All right, I've started recording the session, though I might have loved to get your permission before recording, but let me assume, do I have your permission to record? Just give me a thumb up if I have that. Oh, okay, I can see Peter Joseph's and all right, all right. Okay, yeah, fine, thank you. So on the assumption that we can record the session, later on, I may put a link on your LMS platform for you to be able to rewatch this session. It's fine. I can see your hands. All right. All right, I can see your hands. Okay, you can put your hands down. Those who are raising hands. Tioluwani Bemiga Kaye. Okay. All right. So this is my name, and I hope you can see my screen. This I'm ND Ojo. Okay. So the basic thing we'll be looking at will be acid basis. Then we just look at pH. I want to assume, or maybe even believe, that in your secondary school, you've been introduced to the concept of acid, what an acid is, what the base is. Even in your environment, you might have been familiar with what an acid is. Maybe you have interacted with some of them. So what is an acid? What do we use them for? What is a base? How do we calculate pH? What is the essence of calculating pH? All those things are what you're going to look at in this course. And later on, we'll look at salt, buffer solution, chemical kinetics, and also radioactivity. The objective of this section is to define what an acid is and what a base is, and also to list the properties of acid, bases, and salts, and calculate the pH of strong acid. If you're able to define an acid and a base and list their properties and calculate the pH, we are sorted for today. So let me say that acids, they are just all around us. We live with them. And I want you to type in the, okay, using the chat, just type where we have the chat, some of the acids you know that you can identify in your environment. Some acids you are sure of, you can identify, maybe at home, maybe in your environment, just type them there. Okay, CH3COH, citric acid, stomach acid. Okay, Afolabi, okay. Yeah, you are correct. We have acid in our stomach, and that is hydrochloric acid. Boric acid. So where can we get boric acid? Oh, Oyedele Philip. Ascorbic acid, citric acid, okay. Vinegar, lactic acid. So where can we get lactic acid at home? Is it in sour milk, or where can we get that? Yes, I can see. Okay, H2SO4. Where can we get H2SO4? Palmitic acid, Samic, very good. You are very, very correct. Yeah, you are very correct. Now you see that all of you are very brilliant. And when I was saying that you can get 100% in this course, I actually mean you can get 100% in this course. So you are very, very correct. Some of you may need to check the spelling of your acetic acid. I guess it's AC, not S. Okay, and the battery acid, that is H2SO4. Methanoic acid, well, maybe not very common, but you may be able to get them at home or maybe in your environment. So we have acids all around us, and we cannot do without them. So at the end of this part, you go back to LMS platform. I have left a kind of discussion for you that can we actually do without acid? Can we live without acid? So you go to the LMS platform later after this class, and then let's discuss about it. So just like what you have mentioned, and you are very correct, we have acids from unripe fruits, sour milk, some medicine that we take like aspirin, carbotree, or stomach acid. Even the rain, sometimes it may be acidic. And how do you identify also base? We have also base in the environment. We have what we call the make of magnesia. You know, sometimes when you feel maybe you're having a kind of stomach upset and you go to pharmacist or maybe to your doctor, they recommend some things for you to drink so that they can neutralize the stomach acidity. That can be make of magnesia. And that one can also be a base. We also have base in some of the clean agents at all, or maybe even in our environment. So we have basically acids and bases in our environment. We cannot afford to do without them. And noting that we have all these things in our environment, how can we interact with them? How can we identify them? To your younger, or maybe your younger sibling at home, your uncle, your brother or your sister, how can you tell him or her that this ABC is an acid while DEF is a base? By their properties, you shall know them. So what are the properties of acid and what are the properties of a base? We may need to split it into two, the physical properties and the chemical properties. All right, now let us take a step further. Do we have someone who is not following? Okay, someone mentioned NaCl. NaCl is actually not an acid. It's a neutral salt. We'll look at it, we'll talk about it later when we get to salt. Okay, so we have the properties of an acid. I may even ask you to mention them because you are familiar with them. Acid has sour taste. Concentrated forms are corrosive. They can burn. In fact, if they pour on organic material, they can burn them as if they have been burnt by fire. Then blue little paper, that one, an acid can turn it red, especially when it is moist. And then the pH of acid is less than 7. If you have soluble acids, then they can be an electrolyte. They can be conductors. We also have the chemical properties examples, which are they can liberate hydrogen gas when they come in contact with highly electropositive, that's active metals like a sodium and all that. They can liberate hydrogen gas. And neutralization reaction. Remember then when you were doing titration, maybe in your secondary school days, you might have done something like a neutralization reaction in which you take an acid, you take a base, maybe you put the acid in the burette, you use a pipette to take the base, then you put an indicator, you react them until you obtain an endpoint. That is called neutralization. You might have done something similar to that. Before I take a step further, okay, now type the physical properties of a base. Let me give you that one as what you can do. Physical properties of a base. Can you type it in the chat section? Let me see. Bitter taste, sour taste, no, not sour. Bitter taste is okay. Slippery, soapy to touch, that's fine. They turn red litmus paper blue. Okay, that's correct. Yeah, correct. The pH is greater than 7. That's also very correct. That's correct. What if the pH is 7? What will you say? Then that substance is neutral. But if the pH is greater than 7, then it's most likely a base or maybe an alkali. An alkali is a soluble base that you can dissolve in water, like sodium hydroxide. Okay, they can be corrosive. Yes, if they are concentrated, then they can be corrosive. Yes, you are correct. And the produced hydroxide ion, then you are possibly stepping towards the chemical properties. So let's look at it very briefly. Yeah, I can see your responses in the chat section. You are correct. You're correct. Okay, I guess someone is asking about insoluble base. Okay, when we define base, when we define them more, then you will know which ones are soluble, which ones are not very soluble, which ones are spirally soluble, which ones can easily dissolve in water. So you have mentioned, I guess, everything I have on this slide concerning the physical properties of a base. So let's look at the chemical properties. They undergo neutralization reaction with an acid. So just like an acid can neutralize a base can also neutralize an acid if you react them in appropriate proportion. And you should be familiar with the neutralization reaction, especially if you have a base that has OH, an acid that has hydrogen ion. If you bring them together, you may likely form a salt and also water. An acid can also liberate ammonia gas from ammonium salts when you mix them together. An example is shown on this slide, and they can also precipitate insoluble metal hydroxide. So we have talked about the properties of an acid. We said that by the properties we will know them. You've talked about the properties of a base. You have mentioned most of them. So what is an acid? I know that in the secondary school, you've been exposed to the definition of an acid. Now type it in the chat section what you think an acid is. How can you define an acid? An acid is a substance which dissolves in water to give. What does it give? Okay, put it in the chat section. For those asking for the YouTube link, it's on the LMS, and I've also put it in the chat section. You can follow it either in this Zoom class or also on the YouTube. Okay, proton donor, hydrogen donor, hydrogen ion. Okay, it produces hydrogen ions. Yeah, look at just see the way I pronounce the ions. I call it ions. I didn't call it ions. It is pronounced ions, not ions. Okay, so we have hydrogen ions when it dissolves in water. That is correct. They are substances to give hydrogen ions when you dissolve them in water. They may not be able to give hydrogen ions in the absence of water because they need to dissolve before they can release the hydrogen ions. All right, you are correct. You are very correct. Yes, I can see. I can see your responses in the chat section. All right, let me show you what I have on the slide. So just like what I said, you are correct. And your definition is in line with Arrhenius' theory of acids. That is, acids dissolve in water to produce hydrogen ions. Some also say it can produce hydronium ions, hydroxonium ions, oxonium ions, whichever one you want to call it, you are right. Because the hydrogen ion, when it dissolves in water, it can form the oxonium or the hydroxonium ions. Now that you know this definition of an acid, then we can also classify acids based on whether they have oxygen atom or they don't have oxygen atom. If the acid has oxygen atom, we call them oxy acids. If they don't have oxygen atom, we call them non-oxy acids. Example of oxy acids are H2SO4, HClO4, H2SO3, H3PO4, H3PO3, and so on. So far that acid has oxygen, like CH3COOH, then we can group them as oxyacid. But if they don't have oxygen, we call them non-oxygen acids, like HCl or H high, HCN, and so on. All right. And also we can classify the acids based on how many replaceable hydrogen ions they have, or how many ionizable hydrogen ions they have when they dissolve in water. If they can release one hydrogen ion in water, we call them monoprotic acid. If they can release two, we call them diprotic. Any other one greater than that, we can call them polyprotic acids, like H3PO4. There are some acids that look as if they can release more than one hydrogen ion in solution, but in the real sense, they can only release just one. An example of that is this ethanoic acid, CH3COOH. It looks as if it has 4 hydrogen atoms, but it can only release one out of the 4 in solution. We can also group acids based on their strength. We can have strong acids, we can have weak acid. Strong acids are fully ionized in water, while the weak ones are partially ionized in water. And we have the examples on this slide. I know some of you may have questions. We'll entertain the questions very soon. Okay. So we have the Arrhenius division of an acid. From what you have defined, you said acid is a substance that releases hydrogen ion. So that is Arrhenius theory. So how did Arrhenius define a base? A base releases hydroxide ion in solution, or maybe in water. Acid releases hydrogen ions. Bases releases hydroxide ions. So far, they are Arrhenius acid or Arrhenius base. And here is an example of a strong Arrhenius base, which is a sodium hydroxide NaOH. It can release OH minus when you dissolve it in water. This is a type of reaction you will not like to do at home. And if you come across sodium hydroxide in the laboratory, do not play with it except maybe your instructor or your lecturer asks you to work with it. Because if it is concentrated, then it can be very, very dangerous. It can also be as corrosive as an acid if it is concentrated. Let me also say that there's a difference between concentrated solution and a strong electrolyte. Maybe a concentrated acid and a strong acid. Concentrated base and a strong base. In the chat section, if you know the differences, type it there. The difference between a strong acid and a concentrated acid. Based on what we've been saying so far, you will observe that the definition of Arrhenius is limited to aqueous solution. You have to dissolve either the acid or the base in water before you can have whatever ion it is releasing, whether it is hydrogen ion or it is hydroxide ion. But what if we do not have water? What if that acid is not in solution? Do we have another definition that covers when the acid is not in solution? Yes, we do. And that takes us to the Brønsted-Lowry theory of acids and bases. Okay, I can see some of your chats. Strong, yes. Concentrated acid is an acid that, all right. I guess the way the chat is coming, it's very fast. Maybe I will take my time to read them, but let me assume or let me believe that you're typing something very, very correct there. Yes, strong acid completely ionizes in solution. That is correct. Concentrated one has a little amount of water. Okay, has a little amount of water. All right. Let's take the definition that way. Okay, now let's look at Brønsted-Lowry theory of acids and bases. This is slightly different from what Arrhenius was saying. Arrhenius was defining an acid and a base based on the hydrogen ions or maybe the hydroxide ions, but Brønsted-Lowry was defining an acid as proton donor. This substance, can it release proton? Can it donate proton, whether in solution or out of solution? Can it donate proton? If it can do that, then it is Brønsted-Lowry acid. If it can accept a proton, then it is Brønsted-Lowry base. So a Brønsted-Lowry acid donates proton. A Brønsted-Lowry base accepts proton. And we have an example of that. If you have ammonia, okay, let's say you have ammonia solution in the laboratory, and you also have hydrochloric acid. If you open their containers close to each other, you will observe that the hydrogen chloride gas that comes from the hydrochloric acid and the ammonia gas that comes from the aqueous ammonia, they form a dense white film in between the two bottles. That dense white film is ammonium chloride. The reaction that is occurring there is more or less a neutralization reaction because the acid is reacting with the base. The hydrogen chloride gas acid is reacting with the ammonia gas. Now, see the way I've called the hydrogen chloride. Initially I was calling it hydrochloric acid. That was when it was in solution. Now I'm calling it hydrogen chloride gas. Now in the chat section, give me one difference between hydrochloric acid and hydrogen chloride gas. One difference between hydrochloric acid and hydrogen chloride gas. Okay, the state of the matter. So one is in solution, the other one is in the gaseous form. All right, hydrochloric acid is liquid. All right, let's say it's a solution. Okay, let's say it's a solution. Okay, hydrochloric acid is in aqueous form, while hydrogen chloride is gas. That is correct. That is correct. So when you are trying to use hydrogen chloride and also hydrochloric acid interchangeably, note the state. Note that one is in solution, the other one is a gas. Yes, they are different states. They have different states. That's correct. That's correct. So now we have this type of reaction. I hope you can all see my slide very well. I hope so. Okay. Yes, that's good. That's good. Okay. So we have NH3, which is a gas, reacting with HCl, which is a gas. Both of them are not in solution and they form ammonium chloride, which is a solid. That is an acid-base reaction. That is an acid-base reaction. And the fact that it is not occurring in solution disqualifies it from being a Arrhenius acid-base reaction. But it is Brønsted-Lowry acid-base reaction. So this is what Brønsted-Lowry was saying. And we also have another theory from Brønsted-Lowry, which is a kind of acid conjugate base and all that theory. It's just saying that if you have an acid, okay, let me see if I can use a pointer. Okay, let's see. I guess I can't use a pointer right now. All right, I guess I can use the pointer now. Okay, now let's say we have HCl, which is an acid. It has hydrogen ion. This is H2O. Well, it has hydrogen, it has oxygen. But looking at what they form, this HCl transfers its hydrogen ion to H2O. So this HCl is the proton donor. Let's call it the proton donor. It donates its proton to H2O. And if a substance donates proton, is it an acid or is it a base? Let me get your, okay, acid. Yes, correct. So if HCl can donate this proton to H2O, it means this HCl is the acid. And this H2O, then what is the H2O? The H2O is now acting as the base. The HCl is acting as the acid. Okay, I can see your correct responses. Yes, you know I've said it, you're all very brilliant. You'll get good grades in this course. Now let's look at the right-hand side of this reaction. Here we have H3O plus and a Cl minus. This is a form of reversible reaction. H3O plus, that is oxonium ion, and this chloride ion, don't mind this aqueous, we'll need to make it a subscript later. Now, this H3O plus donates one of its hydrogen ions to Cl minus. If this H3O plus can donate its hydrogen ion, is this a Brønsted-Lowry acid or Brønsted-Lowry base? Is H3O plus Brønsted-Lowry acid or Brønsted-Lowry base? Put it in the chat section. Let me see it. Yes, it is acid. It is Brønsted-Lowry acid because it can donate its proton to this Cl minus. Okay, now so that we'll get it very well. We started from, okay, I can see your responses, you are correct. From this HCl, it has this chloride, but by the time it releases its hydrogen ion or its proton, it becomes Cl minus. So this HCl, which was initially an acid, has become Cl minus, which is now a base. Cl minus is now acting as a base because it can accept a proton. Cl minus can accept a proton. Let me say it again. HCl is Brønsted-Lowry acid. By the time it loses its proton, it becomes Cl minus. This Cl minus is a base. It means that Brønsted-Lowry acid can form a conjugate base. So this Cl minus is the conjugate base of HCl. Cl minus is the conjugate base of HCl. Now let's look at the water. We have said that the H2O, this H2O is acting as Brønsted-Lowry base in this equation. But by the time it gains one more proton, it becomes H3O plus. Initially it was a base. Now it is acting as an acid in form of H3O plus. It means this H3O plus is the conjugate acid of H2O. Let's say it again so that it is very clear. HCl is an acid. It forms conjugate base, which is Cl minus. H2O is a base. It forms conjugate acid, which is H3O plus. And that is the concept of an acid forming a conjugate base or a base forming a conjugate acid. I guess it's very clear. All right, if you understand it the way I've said it, can you just give a thumb up before we move on? Because the next one we want to discuss, oh, okay, I can see your thumb up. Yes, very good. It means you understand the concept. And if you want to rewatch this video, it's on YouTube. The link is on your LMS platform. We have put the link there on your LMS platform. You can always click it and then rewatch the session. The slide is also on the LMS portal. You can get the slide on the LMS portal. All right. Okay. So far, do we have any question? So far, do we have any question? Okay. Emmanuel.
Yes, sir. Good afternoon, sir.
Okay. Yeah, good afternoon, Emmanuel.
Yes, sir. Thank you so much, sir. Please, my question
Okay.
is towards this Brønsted-Lowry acid and bases.
All right. What's your question about it?
You said Arrhenius is for liquid or aqueous solutions.
Arrhenius is
You
for
said
aqueous solution.
yes, sir.
That is, you should have dissolved either the acid or the base in water. Okay, so
Yes, sir.
what's your question?
But I don't understand. This Brønsted-Lowry acid too also deals with aqueous solution, so I'm confused.
Okay, all right, all right. Yeah.
Yes.
Don't worry, I will explain it now in the next couple of minutes.
Okay, sir.
Okay,
Thank you.
yeah, all right. Let me put it back on the display mode. You know, we have talked about Arrhenius acid, and we've defined them based on aqueous solution. That is, whether it is an acid or it's a base, it has to be in water. You have to dissolve it before you can release the hydrogen ion. If that's an acid, or you have to dissolve the base in water so they can release the hydroxide ion. But for Brønsted-Lowry definition, the acid or the base may be in water, it may not be in water. But what we are targeting is, can it donate a proton or can it accept a proton? Let's say that instead of having NH3, okay, let's see if I can use this pointer again. So let's say that instead of having this NH3 in form of a gas and HCl in form of a gas, we have NH3 in form of a solution, that is aqueous ammonia. And we have HCl in form of solution, which is hydrochloric acid. Even if you mix them together, if you react them together, it will form salts plus water. The salt is ammonium chloride, but that will be ammonium chloride solution because ammonium chloride is actually soluble in water. That donation of hydrogen from HCl into NH3 still qualifies the hydrogen as a proton donor, even in solution. And it qualifies the NH3 as proton acceptor, even in solution. So it qualifies NH3 as Brønsted-Lowry base, while it is still Arrhenius base. And it qualifies HCl if it is in solution. It qualifies it as both Arrhenius acid and Brønsted-Lowry acid. So a single substance can be both Arrhenius acid and Brønsted-Lowry acid, or it can be Arrhenius base and Brønsted-Lowry base. Or let's say it this way. All Arrhenius acids are Brønsted-Lowry acids, but not all Brønsted-Lowry acids are Arrhenius acids. All Arrhenius acids are Brønsted-Lowry acids, but not all Brønsted-Lowry acids are Arrhenius acid because Arrhenius acid is limited to water, to solution. Brønsted-Lowry covers both in water and out of water. That is, either you dissolve it in solution, you don't dissolve it in solution. So far you can release proton, it is fine. So I guess Emmanuel understands the concept now, and everyone. All right, I can see another hand up. There's a Afolabi Mary. Afolabi Mary, are you still with us?
Yes, sir. Thank you so much, sir.
Okay.
My question is this. Is it right to say that the difference between an acid and its conjugate base is just a proton?
Or according to the Brønsted-Lowry theory, it is a proton. When Brønsted-Lowry acid loses its proton, it becomes a conjugate base. When Brønsted-Lowry base accepts a proton, it becomes a conjugate acid. So it is based on the proton. Let me take maybe one or two more questions before we move on. Adeniji Emmanuel.
Good afternoon, sir.
Yeah, good afternoon. Okay, Iman,
Yes, sir.
have you know? I think you have had this question before.
No, the surname is different.
Okay. Oh, okay.
Yes, sir. My question is that
All right.
can we? And you said that from the Brønsted-Lowry acid and base, say that the acid will be the proton donor, while the base will be the proton acceptor. And from the equation that you have been giving us, it's like hydrogen is the proton. So can I say that in all Brønsted-Lowry equations, the hydrogen will always be the proton, or just any positive ion?
All right. Just any positive ion. Okay, you can mute yourself now. Proton, the way we define proton, maybe when you move on in chemistry, you will learn more about the particles that make up atoms, protons, neutrons, electrons, and all that. Yes. But in this case, when we are referring to proton, we are referring to something like hydrogen, just hydrogen, actually. We're referring to hydrogen. Not in the ion form right now, but we are referring to hydrogen that has one electron in its orbital. So that's what we are referring to. So whether it will lose the electron later or whatever will happen, then we'll look at that when we're considering the electronic configuration. But by proton, we mean this hydrogen. That's what we mean by proton. Okay, let me take one more question before we move on. I guess I can see is it Iyun? Okay, let's see. Iyun Oluwa. Okay, if you are with us, you can unmute Iyun. Are you with us? Okay, let's look at Gideon.
Good afternoon, sir.
Good afternoon, Gideon.
So my question goes like this. Based on Arrhenius theory, I'm still wondering why it's called a theory, because since his theory is kind of correct, so that's why I'm still wondering why it's called a theory. So please, can you just clarify me on this? Thanks, sir.
Okay. How are you define that? Okay, so why are we calling it theory? Why theory? All right, so that one takes us to the concept of when you start a particular hypothesis, you look at some things you go through. Maybe you have run some experiments and then you come up with a particular hypothesis. Then you start testing them, you allow other people to test them, and it may be acceptable. It may be acceptable within its own limitations. At that point, when so many people have tested it, not just in your own locality, but possibly different places, they have verified it scientifically. It may later on qualify as a theory. But why is it not a law? So what makes the difference between a law and a theory? I may not say that right now in this class, but you may find out when can a theory become a law. Possibly my other colleague might have told you some things about hypothesis and some other steps you go through. But I want to believe that outside of the scope of this course, there are other courses you will take in the university that will guide you on when hypotheses can, through experimentation and other procedures, become theory, and when a theory, through other verifications, can become a law. But we will not so much emphasize that within the scope of this course. But let's take it as Arrhenius, we call it theory, and the Brønsted-Lowry case also we call it theory. Okay. All right, I can see wisdom hand up, but maybe I will take your question towards the end of the class. All right, let's take a step further. We have talked about Arrhenius theory, Brønsted-Lowry theory. Then Lewis theory. So what is Lewis trying to say? Arrhenius and Brønsted-Lowry, they were looking at hydrogen, maybe hydrogen ion, maybe proton, or maybe hydrogen ion. But Lewis' own idea is different from their own. He was looking at an acid or a base based on electron pair. Does it have electron pair to donate? If yes, or does it have electron pair to accept? If yes, then you may look at it as Lewis acid or Lewis base. Lewis acid is an electron pair acceptor. Lewis base is an electron pair donor. Just take the definitions the way they are. Electron pair acceptor, electron pair donor. Okay, so that it will not confuse you with what Brønsted-Lowry was saying. Brønsted-Lowry was talking about an acid is a proton donor. Lewis was talking about an acid is electron pair acceptor. Proton donor, electron pair acceptor. And okay, now let's just use layman definition or layman language.